All right, well, as we get started today, I want to begin by looking at a word problem similar to what we looked at the end of the hour yesterday. We began working on two-digit number word problems, and I say began because we only got through one of them. And there are really three important facts to memorize about a two-digit number word problem. Well, obviously, it's going to involve a number that has two digits. What do we call the two digits that are in a two-digit number, Maddie? You called them the ones place and the tens place when you were in like little kid school, but now that we're bigger, we refer to it as the... One of them begins with a T still, but we don't call it the tens place, we call it the tens digit, okay? And then the other, we don't call it the ones place anymore, but rather the units digit. The tens digit and the units digit. And Maddie, how will we represent the tens digit? I'm sorry? T. And how would we represent the units digit, Maddie? So that's the first two things to remember. That our two digits, the tens digit and units digit, are going to be represented T and U. But we need to remember that the value of the units digit may just be U. But the value of the tens digit is not T. The digit itself will be represented T, but what would be the value of the tens digit? Noah? Since it's in the tens place, as your teacher told you in K5. 10 times the T, right? And so to represent any two-digit number, the actual value of that number, we would represent it 10t plus u. Class, how will we represent the value of a two-digit number? Yeah, there we go. Just reading it off the chalkboard. One more time, class.
10t plus u.
So go and read this word problem for us, Brecken.
The tens digit of a certain two-digit number is 2 less than 3 times the units digit. The number is 10 more than 9 times the tens digit. What is the number?
All right. So as we look at the first sentence, how might we represent that statement, Brecken? Perfect. The tens digit, skip over the prepositional phrase, that's why you put parentheses around those in English class. The tens digit is 2 less than 3 times the units digit. Way to read between the lines there. Now we come to the second sentence, and how would I represent that statement? Perfect. Were we thinking the same thing that Brecken said? 10t plus u, the number, is 10 more than 9 times the tens digit. Were we thinking the same thing he said? All right. What would we do to solve this? Maddie, thoughts? Yeah, we've got a t on both sides here. Let's get rid of one of them, and the little one is the 9t. Let's move that over. What does that make our lower equation become? There we go, t plus u equals 10. Of course, our top equation, t equals 3u minus 2. Thoughts on what we might do next here, Noah? There we go. Let's just do a substitution right here to get
3u negative 2 plus u equals 10.
And of course, from here, we need to combine some like terms, Noah.
4u, and then bring the 2 over as a positive, get equals 12.
There we go. And I like that you did both of those at the same time. That saves me time and trouble of writing stuff, and I'm lazy. Thank you for enabling my laziness. And so we solve in our heads and get for u. u equals 3. So that's not done. I'm not done though, right? There's two digits to solve for, t and u, the tens digit and the units digit. Brecken, now that we know that u is 3, how would I go about solving for t? There we go. Just plug the 3 back into the equation that was already solved for t, and that means t would equal 7. So I'm thinking of a number. The tens digit is 7. The units digit is 3. Let's see if you can read my mind, class. Brecken can read my mind. 73 is our number. Let's check though real quick, because it said that the numbers 10 more than 9 times the tens digit. What would be 9 times the tens digit, class? 63, 10 more than that? 73, it does indeed. Check out. Questions on this type of word problem. You've done a couple of them now. Does it make sense how as long as you've got these facts memorized, it's for the most part kind of plug and play. Let it work itself out. Questions? All right, well, we'll take a look now at a couple of word problems you did for homework last night that had nothing to do with two-digit numbers. And these were on page 179. So if you would turn in your textbooks there, page 179. And you did word problems 11 and 12. They used systems, but not dealing with two-digit numbers. You will have some of those for homework in the days ahead. In addition to that, have your handouts out. You did the even numbered problems from the handout. You went and wrote those right there on the paper. All right, and there's the 21, 23, 25, 27. Good, from the previous day. Thank you, ma'am. All right, there's the evens, there's the 11, there's the 12. Thank you, sir. Are you turning in one of those? Would you care to tear one off and hand it to me?
Yes, sir.
Thank you, sir. Pleasure doing business with you. I didn't want to stay with you. I'm just kidding. All right, let's go ahead and take a look at these together. And number 11, go ahead and read that for us if you would, Noah. This is one of my favorite problems in the book. It's just a really weird problem. Page 179, problem number 11. Noah, read it for us. Thank you, sir.
Farmer Brown has a farm of chickens and cows. The animal heads total 43 and the legs total 124. How many of each animal does he have?
How many, when you first read it, were like, say what now? Just a little bit of an unusual way of looking at things. Animal heads total 43, legs total 124. How many chickens, how many cows does he got? How many unknowns do we have here, Noah? 2, and they are? Good, not heads and legs. We know how many heads, we know how many legs, we just don't know how many chickens and cows. So those should have been our 2 unknowns, and Brecken working it with us now. How did you represent chickens and cows? X and Y. Remember, we said we could use other letters, but in this case, since they both start with C, that makes it a little bit challenging. Now, Noah, we've got to find a way to use the information they gave us. When it says the animal heads total 43, how can I make that an equation?
2x plus 2y equals 43.
So, if I double the number of chickens and I double the number of cows, that'll equal the 43 heads he's got on the farm?
Oh, no.
So each animal has, say, half a head?
No.
No, what should I do?
X plus y equals 43.
There we go. Take the number of chickens plus the number of cows, and that should equal the number of heads because we assume no animal has more than 1 head. Now, if we were on Mars or something, we were raising Martian chickens. There's no telling what we would have. But we're on planet Earth. Each chicken and each cow has 1 head apiece. So if we have X chickens, we have X chicken heads. If we have Y cows, we have Y cow heads, and that equals 43 total heads on the farm, not including Farmer Brown and his family, because it does say animal heads. All right, so there's our first equation. Now we come to our second equation, and we've got to use the fact that the legs total 124.
4x plus 124 equals 124.
So if we take 4 times the number of chickens, that gives us the number of chicken legs?
Oh, wait, no, 2.
Yeah, chickens have 2 legs each. And now I know you haven't had biology yet, so we'll forgive you here. We did have life science a couple of years ago. But anyway, double the number of chickens is the number of chicken legs, right? Now, if you could find a way to make chickens have 4 legs, those of us who like dark meat would be forever indebted to you. Because we buy 1 chicken, get 4 legs. Instead of, how many of you are any of you dark meat people like I am? You like okay. So at Thanksgiving, there's only 2 drumsticks on that bird, right? And there was 5 of us in the family. And I wanted one. And there was somebody else in my family, I don't remember who, there were 2 other people in the family, we all wanted chicken leg. And I was like, but I was the only boy. And so you know how mamas are with their boys, I always got the chicken leg. So anyway, so now I don't buy a turkey at Thanksgiving. I know that sounds sacrilegious. I buy a package of turkey drumsticks. And that's what we serve for Thanksgiving. Everybody got dark meat. And I don't have to worry about it now. And if you're a light meat person, I'm sorry, but I like the tenderness and the moisture and the flavor of the drumstick. But anyway, every chicken, 2 drumsticks, 2 legs, we call them drumsticks. That's number of legs. And then cows, of course, have 4 legs. Now, typically 4 legs, right? If they only have 2 legs and they're both on one side, then you have lean beef, right? And if all 4 legs are missing, then it would be ground beef. Yeah, you all know all the jokes. Okay, so anyway, but we're going to assume these cows, they're just fine, right? All 4 legs per cow. And so that equals our 124. Did you have this system of equations, Maddie? Good, so you were able to read beyond the weirdness of the wording and figure it out. And Noah, we're good now? You know how to figure it out? All right, Maddie, let me go to you then, since you had it, and then Brecken and Noah, kind of Noah fixing his work, Brecken working with us here. Maddie, what did you do next? What did you say? 38 is correct. Okay, I just didn't hear you. And then you divided away the 2 to get y is equal to, which means Farmer Brown has 19 cows. How many chickens must he have then? 24, because he had 43 total heads, 19 cow heads, 24 chicken heads. That is until they pop the chicken heads off. And the little chicken body goes running around for a few minutes, and then plucked and all that kind of stuff, and then we eat it, and you feel somewhat cannibalistic there. Question? It's not. God gave us every beast of the field to eat and enjoy. Amen. I'm not a vegetarian. Any vegetarians in here? No, we all like meat. Amen. All right, questions on number 11. Brecken, any questions? Just lost half my YouTube audience. Gavin's now half asleep. It's like, if you're gonna tell jokes that bad, I'm not gonna. All right, number 12. Go ahead and read that problem for us, if you would, Maddie. All right, this is nice. So now you understand, although it says find the cost of 8 mangoes and 8 kiwis, if you know the cost of a mango, you can find the cost of 8. If you know the cost of a kiwi, you can find the cost of 8, right? So really what we want is not so much initially the cost of 8 mangoes and 8 kiwis, but rather, Maddie, we just need to know how much does each mango cost and each kiwi. Have we all had mango and kiwi before? Okay, we know what they taste like, look like. Okay. So now I'm going to deviate just a little from my usual X and Y-ness here. I'm going to go M and K for my mangoes and kiwis, because M and K don't look like anything else. And so if we go with those letters, how would I set up my first equation, Maddie? And how would we set up the second equation, Brecken?
3m plus 4k equals 7.
There we go. Did we have essentially this system, Noah and Maddie? All right, and Noah, what did you do?
I multiplied top by 3, bottom by 5.
Okay, top by 3, bottom by 5, and that gave you what new system?
15m plus 9k equals 28.
Good, $28.35. And then when you multiply the 5 through the bottom equation,
15 and plus 21 equals 35.50.
all right. From here, Brecken, what would we need to do next? Now let's change the signs across the top equation here. And that'll allow the m's, of course, to cancel. Give me how many k's? 11k. And anyone, when we subtract the 2835 from the 3550, we get 715. Now we need to go ahead and divide out the 11, and this better work out at least to an even cent, or we've got a real problem here. What do we get? 4k. Anyone? We didn't get this far. All right. 11 goes into 71 how many times? 6. That'd be 66, right? So 66 would leave me with 5 left over. 11 goes into 55 5 times. So we should have gotten 65 cents for a kiwi. And we're going to take that 65 cents, Maddie, do what with it? Well, okay, ultimately we're going to have to do that here in just a minute, but I'm not ready for that yet. I still need to find the cost of the mango first, right? So let's go ahead and plug it back into top equation. Put our 0.65 right here. 3 times 0.65, anyone? You carry the 1 on the first one. $1.95. Well, let's subtract the $1.95 from the $9.45 to get $7.50. So if 5m equals $7.50, let's divide the 5 away to get the cost of a mango to be 5 goes into 7 one time with 2 left over. 5 goes into 25. 5 times. Man, we're struggling today. All right, and so we get $1.50 a mango. I'm going to write it with the dollar notation. 65 cents for a kiwi, but that's not what it asked. That's what we needed to find first. But it said how much is the cost of 8 mangoes and 8 kiwis. So you got a big order for the for Miller's grocery or whatever, Miller's Market. So 8 mangoes would be how much money? Multiplying quickly at your seats. $12. How about 8 kiwis? $5.20. And so, how much would it cost for 8 mangoes and 8 kiwis? $17.20. Should have been. Our answer, number 12. It does not appear that anyone here got it. Gavin, maybe you got it. Questions on that word problem? All right, go and have your handouts out from yesterday. Have your handouts out from yesterday. And we were working on our second method of reducing radicals. And we said method number 2 is we don't want fractions. Method number 1, factor up the radicand, take the root of part of the radicand so we can make it smaller. That's one way of reducing, making things smaller. Another way is to make things more simple, and getting rid of fractions is a great way to simplify things. So we said the part of the fraction we're concerned with, class, is the denominator. That's all I care about. I lock in on the denominator. I don't really even worry about the numerator for a little while. I'm focused on the denominator, and we said in order to get the fraction out of the radical, we have to take the root of the denominator. But you can't take the square root of 3. So remember we said, like our days of smashing puzzle pieces till they fit, we're going to go ahead and smash this radical around until we can make it work, not literally, just figuratively. We're going to change the whole radical. Instead of 2/3, we're going to change the fraction so that the denominator is something I can take the root of. And what's a number I can take the root of? 9. I can't take the square root of 3, but I can take the square root of 9. How do I make the 3 become a 9? multiply by 3. But what you do to the bottom, class? Gotta do to the top. So my numerator is going to become a 6. Really, all you're doing is making equivalent fractions, right? Back when you were little kids in 3rd grade, you learned that 2/3 could become 6/9. That's really all we're doing. It's just a strategic equivalent fraction. So that now I can take the square root of 9, class. 3. Nice, easy, rational 3. Can I take the square root of 6? No, but I don't care. I'm just going to leave it as. Now, I did mention if this could be reduced via method 1, factoring it up, then we would do so. But you can't do anything with the 6. We're just going to leave our answer like that. How many had that? For number 2. Number 4, we have the square root of 2/5. Maddie, walk us through. Perfect. Do we get this answer? For number 4. Number 6, we have the square root of 2/7. Noah. Or the square root of 14/49, yes.
And then you take the square root of 49, get 14, or the square root of 14/7.
There we go. Leave the square root of 14 to get the 7 in the denominator to get this answer for number 6. All right, Brecken didn't take time to do it. That's fine. You have the homework pass. Are we following along with what to do here? Number 8, we have the square root of 25/32. Now, we notice we have a 7 multiplied by another 7. You got a 5 multiplied by another 5. You have a 3 multiplied by another 3. And sometimes we get stuck in that rut of just multiply something by itself because that does always work, but it's not always best. I could multiply by another 32 to get 1,024, but I don't want to do that because that's scary. What would be a much better way to go here, Maddie? Multiply it by a 2 so that I get what fraction inside my radical? That is much better, so my denominator comes out to not nearly as scary a number. And for that matter, my numerator isn't so bad either. Now, I do need to reduce the 50 by factoring the 50, Maddie, back into and 25. In fact, we see it here like, oh, 25 and 2, one of those is rational. Well, okay, let's factor it back where we can take the square root of the 25 to get times the square root of the 2. Now, if you left the square root of 50 over 8, really close. You did the main process correctly. We just need to finish out the whole 5 squared to 2 thing, reducing like we had been doing. This would be our final answer. Did anyone get this final answer? You did. Excellent. Noah, did you leave square root of 50 over 8 by any chance? Do you see now just reducing it down? Brecken, any questions on this whole reduce the 50 back down? All right. Let's take a look at number 10. And Noah, we have the square root of 9/10. Walk us through.
I multiplied both of them by 10.
Good. And that is the best choice, right? There are no other squares that have a 10 in them lower than 100.
I got 90 over 1. And then I took the square root of 100 to get the square root of 9 over 10.
Now, Noah, this is very similar to the last one, right? So let's, even though I think you probably stopped here, am I right? Let's keep going now. How can we split up that 90? Don't overthink this.
30 times 3.
Can you take the square root of 30 or 3?
No.
That's not a good way to split it then. How about the 9 times 10 we had earlier, right? And so what would that give us?
3 times square root of 10 over 10.
There we go. Good. Technically, we're splitting. I showed 9 times 10. Technically, it's square root of 9 times square root of 10, right? Which is why we got a 3 times the square root of 10. And this would be our final answer. Maddie, did you go back to back, reducing properly? Got this one, kind of lost out on this one, stopped early? All right, we understand it now. And then again, Brecken, understanding, following along here. All right, and then number 12, a cube root. Oh boy. We have the cube root of 5/12. I don't have a whole lot of cubes, right? What's my smallest cube, of course? 1, right? 1 cubed is 1. Okay, what would be the next cube? 2 cubed. 8, there we go. So 1, 8, what comes after 8? 27 would be 3 cubed. 64, could 12 turn into either of these? No, okay, let's keep going. What's the next cube? 125? No, can't turn into that. What comes after that? 216. Could 12 turn into 216? Does 12 divide evenly into 216? Let's see, 12 would go into 21 one time with 9 left over. Bring down the 6. Come on now. Does 12 go into 96 evenly? How many times? Okay. So, yeah, 12 times 18 would give us that denominator of 216. Did you figure that out? Doesn't seem like it. What did you do with this, Maddie? But you see 24 isn't a cube, so that's no good. What did you do, Noah? Okay, now that does work. Noah said I've got a 12 here. If I multiply by 2 more 12s, I'll have 3 of them, 12 cubed. So we multiplied by a 144 to get, I think that's 1,728, which works. It just means you've got more reducing to do up top. Let me show that method here in just a moment, but for now let's roll with the easier method here. 5 times 18, anybody? 90. And now this time, you can't factor a 90 for a cube root, because none of your cubes are in 90. So we're going to leave the cube root of the 90 and put it all over the cube root of 216, class, which is 6. And there's our answer. Noah, that's what you should have ended up with eventually had you taken the time to reduce your work down. Let me show Noah's work very quickly. And again, it's not a bad strategy. I've got 112 here. If I multiply by 2 more 12s, then I will have the cube of 12. So I'll be able to take the cube root of it and get 12. Do you see the logic he was using? He then would have had to multiply the 5 times 144 to get 720. And I'm assuming you left your answer this way. Yeah, probably not seeing that you could actually factor that into 8 times 90, where you can take the cube root of 8 to get 2 times the cube root of 90 all over 12. And now the 2 and 12 reduced with each other and would have given us that. Okay, but I like that you were on the right track there. Good job. Questions on this? All right, set those. Actually, if I collect the handouts, let me go and collect those handouts back from you, since I'm lazy and don't want to reprint them for next year's class. Just pass the Corona on to somebody. Just kidding. They sit in a file cabinet and the Corona dies. So I think they say Corona doesn't last on paper for more than like 2 or 3 days. So yeah, Corona will be dead before we give it to the next kids. All right, let me give you some classwork to practice on the various methods of radical reduction we've had so far. Let's start with our first method, factoring up the radicand. At your seats, reduce these 5 radicals. Again, if you need to, make a list of your cubes or a list of your squares and things of that nature, by all means, do so. All right, for the sake of time, pencils down, even if you're not finished. Let's take a look at the ones you got done. I first want to point out that a list of cubes for a cube root may be very helpful. 2 cube, 3 cube, 4 cube, 5 cube. You don't have to write them all out, but maybe list the first few. That helps you to literally see your options. And you look at it, and the only one that looks even remotely good is the 8. 8 goes into 72, 8 times 9, 2 times the cube root of 9. Are we good on the first one? Questions on the first one. Looking at the next one, it's a square root, so perhaps make a list of your squares. 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, maybe just the first few. And, well, I know there's a 4 in there, 4 times 21. 2 times the square root of 21, and there's no more of these inside of 21, so I guess I'm done. How many had 2 times the square root of 21 for the second? On the third, go back to your list of cubes. 8, 27, 64, 125. Well, 125 is bigger than half, so I know that can't be it. 64 is not half or third, unfortunately. 27? Yeah, 27 times 7, there it is. But again, seeing your options helps you not to be like, I don't know. When you have a list, it helps your mind to focus. 27 times 7, take the cube root, get 3. Times the cube root of 7, how many got that for the third one? Questions on that one? On the fourth, now, if you made the whole list of cubes, you would have been fine. But hopefully, as you saw 3,000, and it's a cube root you thought of 1,000 times 3 to get 10 times the cube root of 3. How many had that for the fourth one? Questions on that? And then on this last one, it's a fifth root. Now, I don't have a big old list of memorized fifths. Cubes, yes. Squares, yes. Fifths, no. Obviously, I know 1 to the 5th is 1, but that's no help, right? 2 to the 5th we've memorized, that's 32. I went ahead and figured 3 to the 5th and realized, whoa, that's 243. That's obviously not a factor of 160. It's bigger than 160. It's got to be 32. Yep, 32 times 5. 2 times the 5th root of 5. How many had that for the last one? Questions on these? Questions on these? All right, let me give you a few more, and this time involving letters. And remember, to take the root of a power class, you will... To take the root of a power, you divide the exponent by the index. How many times have we said that? A bunch? Yeah, you should have that memorized by now. Let's say it together one more time. To take the root of a power, divide the exponent by the index. I couldn't hear anybody but myself. That's a shame. Let's say it again. To take the root of a power, divide the exponent by the index. Memorize that statement if you have not already. Now, you're still going to have to factor the number. But as far as the letters, simply say, how many times does this go into that? What does the 1/3 power literally mean, class? Oh, it's been a while. Glad we're reviewing this. It's just another way to say the cube root. It's the cube root of all of that to the first power. And anything to the first power is itself, so it's just the cube root. So on the next one, what does the 1/2 power mean, class? Square root. Just another way of saying it. Go ahead and put your pencils down. Even if you're not finished, check your answers. Here, factored into 27 times 5, got a 3, left the 5. 3 goes into 4 one time with 1 left, 3 goes into 5 one time with 2 left. Did we get this answer on the first one? On the next one, 8 times 2 is pretty evident. So I got a 2, and I left that 2 inside. 3 goes into 5 one time with 2 left, 3 goes into 9 3 times with nothing left. Did we get this answer? For the second one, 2mn cubed times the cube root of 2m squared. On the next one, it's a really big number. So instead of just going through 4, 9, 16, 25, I'm like, I'm going to be here all day. So I'm like, well, can I cut it in half? No. Can I divide it by 3? Yes, but 135 doesn't do me no good. How about dividing by 5? Again, skip over 4 because it's a square. 81. Ah, there it is. 9, leave the 5. 2 goes into 5 twice with 1 left. 2 goes into 2 one time with none left. Did we get this answer? 9a squared y times the square root of 5a? When it's a big number, switch to this method. Oftentimes it'll be quicker for you. And then our last one, we didn't have to factor 32. We can take the fifth root of 32, that's just 2. 5 doesn't go into 4, 5 doesn't go into 2, but 5 does go into 5 one time with nothing left. There should have been our answer to the last one. How many had that for the last one? Questions on these? All right, let's do one more quick run through with the fractions like we had last night in our homework. Again, we have to take the root of the denominator. That's really all we care about. Though, if we could reduce the numerator, sure, let's do it. But we really care about taking the root of the denominator. If you can't take the root make it where you can take the root. All right, check your answers. Do you notice this one's already good? Just take the square root of 4 to get 2, make the square root of 3. This one, I need to multiply by 5 to get 20 25ths, gives me the square root of 20 over 5, but I can factor that back up into square root of 4 square root of 5 to get 2 times the square root of 5 over 5. Did we get that final answer, or did we stop too soon? How many got the final answer? How many stopped too soon? Careful. All right, looking at the next one. Did we identify 8 was our number of choice here? It's a cube root, so 4 is no good. Get the cube root of 6 over 2. And on the last one, 32. Do not factor it. I don't care that, hey, that factors at 8 times 4. We ain't doing that. We factor radicands, but not when it's a fraction. We take the root. Don't factor it. Multiply by 2 to make it an even rational root, or we can get cube root of 10 over 4. Did we get that answer for the last one? Excellent questions on this. All right, in your notes, reducing radicals, part 3. Reducing radicals, part 3. And this, to me, is the easiest of the 3 levels. Reducing radicals, part 3. We've talked about making the radicand smaller. We've talked about getting rid of the fraction from the radical if there is one. But for part number 3 in reducing radicals, we want the smallest index possible. Not only do we want a small radicand, we also want small indexes. Basically, class, square roots and cube roots are happy because we know a lot of square roots and cube roots. 4th, 6th, 8th, 9th roots. Those are frightening to us. We don't like big indexes. So if I saw something like the 15th root of 27, write that down, that's slightly terrifying. Would we all agree? Slightly scary. We want to make the index smaller. Watch what we may do. Well, first of all, the key, if you'll write this down, is to rewrite the radicand as a power. Rewrite the radicand as a power. I'm going to rewrite my 27 as 3 cubed. This is why, sound like a broken record here, it's so important to have these memorized. You have no problem when you see 27 and be like, oh, that's 3 cubed, if you have them memorized. At this point, I could and I normally wouldn't, say, well, let's write this like a fractional exponent, right? Divide the exponent by the index, 3 to the 3/15. Why, lo, I can reduce this. I can call this 3 to the 1/5 power, right? In which case, this could be written the 5th root of 3 to the 1st. But I generally don't do all of that because I'm lazy. If I can reduce 3 and 15 in a fraction, I can reduce 3 and 15 here and say, hey, let me knock a 3 out of that and a 3 out of that. Oh, look, the 5th root of 3. Now, doesn't that look less scary than the 15th root of 27? So the key is to rewrite the radicand. Your second step is to cancel factors out of all the little numbers, meaning index and exponent. Cancels common factors out of the little numbers, meaning the index and the exponent. Write this down if you would. The 10th root of 361. The 10th root of 361. Now 361 is a special number. What is it, class? It's 19 squared, and we should have that one memorized. It's 19 squared. So what I'm going to do, class, is I'm going to see, look at my little numbers. Stay with me. One's a 10, one's a 2. What can I take out of both 10 and 2? 2. If I take a 2 out of the 10, what do I get? 5. Take a 2 out of a 2, I get a 1. Dividing, taking out, meaning dividing out, which means I've got the 5th root of 19. Still somewhat scary, but not nearly as bad as the 10th root of 361. Write this one down. The 6th root of 125. How can I rewrite 125, anyone? 5 cubed, good, Brecken. And looking at the little numbers, what can I take out of 6 and 3? 3. If I take a 3 out of a 6 class, I get a, and take a 3 out of a 3, I get a. So in other words, my answer is just square root of 5. I'm going to leave the index and exponents understood. One more, and I'll let you go. Write this one down. The 6th root of 36, a to the 4th. How can I rewrite the 36? I'm sorry? 6 squared. Again, the key is to rewrite the radicand as a power. Now notice this time, class. I'd have a letter now, right? I've got a letter. So now I don't just look at these two, it's got to be all of them. What can come out of 6, 2, and 4? A 2. And I've got to take a 2 out of every single little number. Does that make sense? What do I get when I take a 2 out of a 6? When I take a 2 out of a 2? And a 2 out of a 4. So how will I write my answer, Maddie? And there we go. Do we see what we're going to be working on tomorrow? All right, now homework this evening. Have a wonderful rest of your day, and you are dismissed.